from yesterday timetable has been changed, right? So I have scheduled the meeting for B section. Might be they have attended, they might have gone into that one. Okay, so I just start with the today's class, and before that I'll just go through what we have discussed in the earlier class. So in the previous class we were discussing about uh, class A amplifier. So in that class A amplifier, when we are discussing, so we have seen that it is class B again. Okay, I'll just orally will tell. So what is class A amplifier? And in the class A amplifier, when we are discussing, so we have seen emitter follower configuration. So with a constant biasing mechanism we have employed, so that for negative power supply, since the emitter follower is whatever the input you are going to give, so it is going to get reverse bias. That is, the transistor Q1 is going to reverse bias during the negative half of the cycle. So because of that, what will happen? So during the negative half cycle, so there will be no current flowing between the across the load. So for that constraints, so in order to make the 180 for the 360 degree complete full cycle output, so what we have done is we have connected a constant current circuit, so which is going to maintain a constant current which will be greater than the negative load current which is going to flow. So during the negative power supply, during the negative half of the cycle, so we know that it is emitter follower configuration. So wait a minute, I'll just go through that one. Class A amplifier topic with that. So class A amplifier here at the top. Okay. So I'll just discuss overall. So class A power amplifiers, when we are discussing, so emitter follower configuration it was there. So emitter follower with a constant biasing and across the load. So during the positive power supply, so the input is going to play and you are going to get the output. So if you see the transfer characteristics, you can see the slope is equal to 1, right? So slope is equal to 1 indicates what? So that means it is a emitter follower configuration, so that the output voltage will be same as that of input voltage. So as soon as you increase the output voltage, so it will start increasing increasing in the voltage term. So based upon that, so we have started with here only I just okay. So in this class A amplifier, so since this is a common emitter configuration and you are going to connect an external load resistance over here, so the current during the positive half cycle you will be getting the transfer characteristics over here, this like. So only the input voltage greater than VB will be starting producing the output. So output voltage with respect to input has been plotted. So as you increase the output voltage, so you can see the slope is 1/1. So this indicates what? It is a emitter follower configuration, and the output is going to follow the input. So we are going to get the slope as equal to 1. And since the input voltage can be swing, and whenever the input voltage is becomes equal to the maximum value, so that means the transistor will enter into the saturation at that instant. So you can see the output voltage will become saturated in the positive way in the VCC minus VCE is one saturation. And then so similarly, if you are going to apply that during the negative half cycle, so the maximum load current, so that can be given. So during the negative half of the cycle, so this transistor Q1 will be cut-off region, so that because it is going to have a reverse bias over here, so it is going to enter into cut-off state. And only because of transistor Q2, so the current it is going to be flown over here. So the current which is going to flow, it will be equal to I times of RL. So only thing is that the current I will be constant, and this current is going to limit the output voltage. So since the current flowing is it is constant, I is flowing. So the current, the voltage across the RL, So the current across the RL is going to be equal to I times of RL. So this is going to limits the limits the maximum negative current flowing across here. But if you change the order of this one, so that you can, if you are increasing in the negative direction more, so that the input will reach to the maximum value, so that the transistor will enter into saturation. Up to that point, you can increase in the negative direction. So this is one minimum negative output voltage value will be determined by the I into RL. Whereas if you still increase the reverse bias diode, if you are going to increase the voltage, then you are going to get the output voltage to reach maximum up to minus VCE plus VCE saturation. So VCE to saturation. So this is the maximum negative voltage swing, and this is the maximum positive voltage swing. And then we have seen the different waveforms with respect to output voltage as well as the collector to emitter voltage and the collector current. This is nothing but output current, and this is nothing but the collector to emitter voltage. And we have seen the output voltage from the transfer characteristic itself. So it will be reached maximum up to VCC minus VCE saturation. So neglecting the VCE saturation, so you can see the positive peak can be reached up to plus VCC, and negative voltage can be reached up to minus VCC. So that we will be getting maximum output voltage starting from 0 to maximum positive peak and negative peak. So and then we have seen the collector to emitter voltage drop. So in that collector to emitter voltage drop, we know that so collector to emitter voltage is nothing but what? So this is the VCE. So VCE will be equal to VCC minus V0, and if you see, the VCC will be constant and V0 is going to increase upon giving the input voltage. So in the initial stage, V0 will be equal to 0 when VA is equal to 0, or VI is less than VB1, so the output voltage will be 0. So in that case, the output voltage, that is the VCE, will be maximum, that is equal to VCC. And then as the output voltage starts increasing from 0, and VC, collector to emitter voltage, also it will start reducing, and it will reach to 0 when it is reaches maximum positive peak VCC. And similarly, as you increase, as the voltage keeps on decreasing, and when it reaches to the negative voltage, so you will be getting the output voltage, collector to emitter voltage, to be of 2 times of VCC. At the same time, so output current is also, it is going to start at the base position as I, because of Q cent point. So when you are going to select a Q point at the certain operating point at the center of the load line, so you can see that there is corresponding current flowing inside that due to DC biasing will be starting with a certain reference level that will be equal to I, and it is not equal to 0. And you can see that as you increase, so the current will be increasing up to maximum value up to 2 times of I, and it will reach to a minimum value of 0. So this is the graph which you are going to get for the output collector current, and this is the graph which you are going to get for the collector to emitter voltage. And the ratio of, when you multiply, we want to find that instantaneous power distribution for class A stage amplifier. So PD1, which is going to be equal to VC1 multiplied with IC. So if you multiply this, you will be getting the instantaneous power dissipation, and this is the maximum instantaneous power dissipation, that is equal to VCC into I, and this is going to happen at when the input voltage is equal to 0. So whenever the corresponding input voltage is equal to 0, so you are going to get the power dissipation, maximum power dissipation at when VI is equal to 0, or when there is no input signal. So because of that, you are going to get maximum. After that, you can see there is a reduction in this one. So this can be considered as the maximum power dissipation, and we have seen the current as well as power dissipation expression in this one. So in order to find out the power dissipation to the load, so we are going to consider two cases for this. So when RL is equal to infinity and when RL is equal to 0. So when RL is equal to infinity, that indicates what? So that is a open circuit. Okay, so when it is open circuit, so maximum you can say that the power dissipation due to maximum power dissipation will be delivered to the load will be equal to, so that is depend upon the IC is equal to I, and it depends upon the positive half cycle and negative half cycle, what is the amount of power delivered, and it will be equal to 2 times of VCC into I. So this is the power dissipation when RL is equal to infinity. When now consider the case when RL is equal to 0, that is short circuit. So in that center, so maximum amount of current is going to flow across the load. So because of short circuit, there is a negligible resistance, and the RL is equal to 0, and hence there must be certain protection circuit for the A class A amplifier in order to avoid that much large current. So that is about the class A amplifier stage. And then coming into the second case, in order to increase the output stage of the, it is the efficiency of the amplifier. So in order to increase the efficiency of the class A amplifier, which is equal to 25%. So maximum conversion efficiency is equal to 25 in the case of class A. So what we are going to do? So we are going to employ a transformer coupled based power amplifiers. In this transformer coupled amplifier, power amplifiers, what we are going to do? So in place of static resistance where it was having RC, there is a collector resistance was there. So where there you are going to employ a transformer based coupling transistor over here. So in this case, what will happen? So the same RC coupled amplifier is there, and in place of collector resistance, which is going to not to increase the maximum efficiency, conversion efficiency, we need to match the impedance between the output resistance and the actual load resistance. So if you match this one, so then you will get a maximum conversion, power conversion efficiency will be increasing. So for that purpose, we are going to remove that collector resistance, and we are going to employ a transformer, so which is going to have a primary winding across the circuit and secondary winding across the load. So N1 corresponds to the number of primary winding, and V1 is the corresponding input voltage, and I1 is the corresponding current that is flowing across the primary transformer. And in the secondary transformer, the number of turns is denoted as N2, and the output voltage is V2, and the current that is flowing is I2. So with this the current voltage as well as number of turns, so we can say that it is going to have a relation between the input voltage, current, and the primary winding and the secondary winding. We are going to have a number of turns with the input voltage as well as with the voltage, and the number of turns with the current. So that is given with this expression, and with this expression we can say that in order to match the impedance matching, so what you should have? So you should have V1 by I1. So here as I told in the previous class itself, so it is mistake is there. So V1 by I1 must be equal to N1 by N2 whole square into V2 by I2. So this indicates what? So V1 by I1 is nothing but input resistance, that is which you are going to call it as a effective resistance. So effective load resistance RL dash, and this is the actual load resistance RL. So this need to be matched with this so that maximum power can be converted, and it will be transmitted to the load. So V1 by V2, V1 by I1 should be equal to V2 by I2 into N1 by N2 whole square. So this is the maximum how the impedance need to be matched. So this is how we are going to match. So this is the number of turns we are going to match with respect to the load resistance. So this is how the relation it is going to hold. So if this equation is going to hold good for this transformer, then you will be getting the maximum power conversion efficiency. And with this consider, so this is an ideal case of transformer we are going to consider. In this ideal case of a transformer, so what will be the voltage across these two, V1 and V2? So DC voltage will be absolutely zero. So if the DC voltage is absolutely zero, that means that the resistance is also equal to zero. So when you are going to have a DC operating condition, so we have to see DC operating condition as well as AC conditions, right? So first we are going to concentrate about the DC. So when you are going to consider DC conditions, operating conditions, so the V1 and V2, so there will be no voltage to be developed across here. So because of which what will happen? So V1 and V2 will be equal to zero. So because of which the resistance associated for the DC load will be equal to zero. So if it is a resistance so if the load is zero, then what will be the slope line? Slope line will be crossing in the vertical way. So instead of slanting lines in the previous case of class A amplifier, so you will be getting it is in the going to, you can see this is nothing but this is a vertical line which is going to be connected, that is going to operate with and the slope will be equal to infinity. So 1 by minus 1 by RL. So DC load line will be having the slope of infinity, and this is the operating point Q, and this is corresponding current that is flowing, and this is a corresponding voltage that is going to have. So at this corresponding point, as we have seen in the previous case, so it is going to be equal to VCC. So VCC will be the DC supply voltage, so that is equal to VCC, and ICQ is the current that is going to have. And now if you consider, so the AC conditions characteristics, so AC condition will be having the same as is a minus 1 over RL. So for this AC condition, so you're going to have a DC AC load line to be flowed across this one. So whenever there is an interaction, so intersection of this AC load line and the DC load line, so we are going to select that Q point operating point, and this operating point so is where we are going to have an intersection of DC load line as well as DC load line. And you can see this is the amount of current that is flowing during the AC load current, and this is the maximum peak in the negative direction, and this is a maximum peak, and this is the maximum output current, so output voltage with respect to this DC load line as well as AC load line. So this is the maximum input current which is going to vary. And now if you consider the efficiency, so after finding out this and down, so we are going to find out the conversion efficiency. In order to consider the conversion efficiency, so we already know, so what is the AC power delivered to the load and the DC power supplied. So that is the supply power in DC and the AC power delivered to the load. So that is the ratio of AC power delivered to the load to the DC supply power. So that is given as the efficiency. So this efficiency is given by PAC by PDC. So DC power supplied, what is the DC power supplied? So this is the VCC is the voltage and this is corresponding current. So that is the ICQ. So VCC into ICQ is the DC power supply, which has been seen in the from the graphical characteristics. And what is the AC output power? So AC output power is nothing but AC power delivered to the load will be equal to VRMS into IRMS. So what is VRMS? VM, peak to VM divided by root 2. So this is the maximum peak and this is the negative peak. So Vm divided by root 2 into IRMS is Im divided by root 2. So this is the AC power delivered. So this is the DC power delivered. So we're going to see VCC by root 2 into ACC divided by root 2. So in terms of peak voltage, what is the Vm corresponds to? Vm corresponds to the peak of the positive peak as well as negative peak. So we're going to have a maximum positive peak as a VCC and a negative peak as VCC. So VCC divided by root 2 is the maximum peak of the voltage and maximum peak current is given by ICC. So ICC into ICC divided by root 2 and VCC divided by root 2. So divided by ICC into ICQ and multiply with 100. So this you can give the transformer coupled efficiency as equal to 50%. So this is the efficiency, maximum efficiency which you are going to get when you are replace the RC coupled amplifier with the transformer coupled class A amplifier. So this is also class A amplifier itself. So only thing is that we have just replaced with transformer coupled. So this is about the class A amplifier, transformer coupled class A amplifier. Okay. So any doubt is there in this? So we can go for the class B output stage. So class B output stage. So what is the class B amplifier? So in order to understand this, first you should know what is the classification, how we have done for the classification for the class B amplifier. So class B amplifier has been considered based upon the operating angle. So how the operating angle we are going to see. So operating angle means so you have to consider this the operating angle. So in order to understand the operating angle, what you should do, so we have to go through this output voltage and current characteristics, and this is the output curves which you are going to get, and this is the Q point for a class A amplifier. So for class B amplifier, where you are going to select, so class B amplifier, we are now we are going to study up the class B. So the class B amplifier Q point is selected as a point at the cutoff point. So this is the cutoff region for the BJT. Since you are going to see, so this is a BJT for collector to emitter as well as collector current characteristics, in which x-axis and it corresponds to the cutoff point, wherein which there will be no output current. So this is the cutoff point, and this is nothing but a saturation point, and this is nothing but a linear region. So in this linear region, you need to select in order to consider it as an amplifier. So in order to consider this as an amplifier, we are going to select the Q point at the center of the load line for class A. So for class B amplifier, what I have just told, so the class B amplifier, so the operating point must be considered at the bottom, that is the x-axis line, that is the cutoff point. So in this point, if you are going to select the Q point, then what will be the result? So what will be the result? So this result will be, you will be having only positive half cycle to be passed and negative half cycle will be getting clipped off. That means during the whatever the input if you are giving, so only the positive half cycle of the input you can get at the output. So whereas negative half cycle, so it will be clipped off. So this is what you are going to understand with the class B amplifier. So now class B amplifier is considered. So in that class B amplifier, so what I have told, so there will be only 180 degree. This is a 0 to pi. Operating angle will be 0 to pi. That means 180 degree. Okay, so only 180 degree. So if I want to get a full output wave cycle, so what I have told, so in order to get a full output wave cycle for a given input cycle, so what I need to do, so I need to do, I need to consider another class B amplifier which is going to work in opposite to that of the previous class B amplifier. So in that case, if the both class B amplifier is given with a common input, so that during the positive cycle, one of the class B will be delivering the current to the load, and another during the another negative half of the cycle, another class B amplifier is going to deliver the current to the load. So in that case, you're going to consider two stages of class B. You're going to consider in order to get the full complete output waveform of 360 degree. So for a given input, for a given full cycle of input, so if you are going to consider only class B, means you will be getting only 180 degree. So in order to get the full output, so I need to consider two class B amplifier. So one will be providing during positive cycle and another will be providing during negative cycle. So total of 360 degree will be getting. That is nothing but a total output if I want to get. So I need to connect to class B. So each class B must be opposite to each other for in operation. So the same class B output stage we are going to consider now. So we are going to see what type of the circuit you should have. So as I mentioned, so in this you can see the class B amplifier consisting of a complementary transistor. So this is nothing but a complementary transistor. So connected in such a way that both the way it is going to be connected. So input will be connected for both the transistors simultaneously. And we are going to have a load resistance RL connected at the output of this configuration. So what is the how it is going to be considered? So again, if you consider, so this it will be considered as an emitter follower stage itself. Okay, so both the base of terminal of transistor Qn as well as Qp. So Qn corresponds to NPN and Qp corresponds to PNP transistor. So both the base of the transistor will be connected and it will be given as an input. So why it is called as complementary? Because both NPN and PNP has been used together. So why we have connected complementary? Because so during the first half cycle, that is a positive half cycle, your NPN will be conducting, and during the negative half of the cycle, PNP will be conducting. So since we have just used both the transistor given with the input signal, so you will be getting the complementary. So complementary in the sense, so you know that complementary means another name for complementary is nothing but inverter. So whatever you give the input, so you will be getting the output as over here. So that means the output will be inverted version of the input. So Vi is equal to 1 output will be 0. So if Vi is equal to 0, so output will be 1. So that is nothing but a complementary pair of transistor. So here complementary pair in the sense, so both will be having in opposite characteristics. So Qn is opposite to that of Qp characteristic. That is the NPN is opposite to that of PNP transistor characteristics, and Vi as an input signal and Vout is nothing but output signal, and the output across the load resistance has been connected over here. So this is nothing but a complementary. So we will see the circuit operation now. So what will happen whenever we are going to have this? So you are going to consider, so whenever we are going to have a input voltage Vi is equal to 0, and if it starts whenever Vi is equal to 0, so we can say that Qn as well as Qp both will be operating in cutoff state. So both the transistors will be in cutoff. That means both will be in off state. So there will be ideal what is the output voltage? So output voltage will be equal to 0. So we'll be having V0 will be equal to 0. So when Vi is equal to 0. So now whenever the input voltage is going in positive direction, we know that it is nothing but a Vi is nothing but what? So it is the instantaneous input voltage, and this V0 is nothing but a instantaneous output voltage, instantaneous load current, and this is a DC negative DC power supply, and this is a positive DC power supply. So positive must be given to the NPN transistor, and negative must be given to the PNP transistor. And now when the input voltage is 0, so what will be the case? So both will be off, and when Vi is going to increase in positive direction, what will happen? So whenever I am going to give a positive input for this one, so the same positive will be given for QP base as well as QN base. So Qn will be start conducting, because so Qn requires how much the input voltage must be greater than the base to emitter voltage. That means it should be greater than positive. So positive, if we are going to apply the positive input voltage, whenever it is greater than VBE, so you know that base and emitter here it is. So base to emitter voltage kinta jaasti ichu, then obviously this Qn is going to turn on. So less than VBE, so even this Qn will be in off state. So same thing, so you have to analyze this for the QP transistor, that is PNP transistor as well. So whenever the input voltage is in moving in positive direction, so what will happen? So this is becoming the positive, and this is the negative. Reverse voltage is what? So the out VBE will be in negative. So when you are giving the positive, then also the transistor is going to be operating in reverse bias only. So whenever you supply a input voltage greater, that means in a negative way. So if the input voltage is in the negative greater than minus VBE, then only the QP transistor will be on. If you are going to supply positive, means obviously this will be in on off state only. Okay, so you need to supply a voltage which is greater than, so minus VBE in the reverse direction. So that means minus VBE minus 0.7 ಅಂತ ಆಯ್ತು ಅಂದರೆ, so minus 0.7 ಗಿಂತ ಜಾಸ್ತಿ ಕೊಡಬೇಕು. So then only, so you are going to turn on the this PNP. So if you are giving positive, means obviously this QP will be in off state only. So whenever the input voltage is less than VBE, so QN also it will be off, and whenever the input voltage is greater than VBE 1, so then only you will be getting the output voltage. So what will be the state of this condition? So if you consider this state, so this is nothing but a emitter follower configuration, because whatever the input you are going to give at the base terminal you are giving, and at the emitter you are going to get the output. So this is nothing but a emitter follower, and the output is going to follow the inputs case. So when it is going to follow the input, so only when the input voltage is greater than VBE, then the output voltage is going to have a follows the input signal. So this is the operation of this transistor QN. And now, so when you are going to apply during the negative half cycle, what will happen? So during the negative half cycle, so this comes less than minus whenever the input voltage comes less than VBE1, so obviously this QN will starts conducting, and this will enter into cutoff state. And at the same time, so whenever the input voltage is equal to 0 or less than minus VBE1, so VBE2 minus VBE2, then QP also the transistor will be in cutoff state only. So cutoff means it will be in off state only. Whenever the input voltage increases just below minus VBE1, that is minus in just above the minus VBE1, so then your transistor QP will be on, and this is going to this will be on, and it is going to supply in the reverse direction. So that is nothing but so during the positive cycle, so QN is going to push the output voltage with the load current, so IN. So the current is going to be flown through the positive power supply, and during the negative half cycle of the input, so it is going to pull. So it is called, this is called as a push-pull configuration. So the same thing it has been written over here, circuit operation. So when Vi is equal to 0, so both the transistor will be cut off, output voltage will be 0. So whenever the input voltage positive and exceeds about 0.5, so exceeds about 0.5 means here VB will be equal to 0.5 in the, so whenever the input voltage exceeds 0.5, the QN conducts and operates as an emitter follower, and we can see V0 will be equal to Vi. So that means the output is going to follow the input. So Vi minus VBN, so that is the VBN drop will be there. So the output is going to follow. After that VB1, so output is going to follow with respect to input. So QN supplies the load current, and hence emitter base junction QP will be in reverse bias, and it will be in off state. So whenever the input goes negative, and if it is greater than 0.5, so if it is greater than 0.5 means in negative way. So if it is greater than negative 0.5, then you are going to get the output. So then only you will be getting the output. Again, in this case also, this QP transistor is operating like a emitter follower configuration only. So in this emitter follower configuration, the output is going to follow the input signal. So in that case, QN will be in cutoff. That means transistor QN will be cut off, and QP supplies the load current from the negative power supply. And hence we can say that class B stage, so whenever it is biased and zero current, so current only conduction will be current only when the input signal is present. So the circuits operate as a push-pull configuration. So push-pull means QN pushes the current into the load, whereas during the positive cycle, and QP pulls the current from the load during the negative cycle of the input. So this is what the push-pull configuration. So now if we understand, if we go for the transfer characteristics, you can see this is the transfer characteristics of class B amplifier for the complementary transistors which you are going to see here. So from the stage 0, so you can say that transfer characteristic means, you should remember, so this is the bottom output voltage versus the input voltage, whatever the characteristics which you are going to have. So that is the remote term transfer characteristics. So that is output, the plotting of curve with respect to output voltage and input voltage is nothing but a transfer characteristic. And you can see, so this is output voltage and this is input voltage. So whenever the input voltage, you have to assume this transistor, so complementary transistor. So whenever during the positive half cycle you are going to give, so you have to understand this is the QN transistor, you should remember, and this is the corresponding output voltage we have to consider. Okay, so this is the, whenever the input voltage is greater than 0.5, because this is the base to emitter voltage, so this QN transistor. So whenever the input voltage is less than this 0.5 volts, so whenever the input voltage is less than 0.5 volts, so obviously what will happen, so the transistor, so BJT will be in off state. So BJT will be in off state, QN will be in off cutoff state, and whenever the input voltage is exceeds the 0.5, then you can see the output is going to increase with respect to input. So the slope is equal to 1 indicates what? It is a emitter follower configuration. So output is going to follow that same as that of input. So output slope will be having what? So output with respect to input, if you plot the slope, so slope will be equal to 1, and you can see the increase in the output voltage with respect to input, and the output will get saturated. So after that, if you increase the input voltage still further, the output voltage will get saturated because the transistor entering into saturation. So at that stage, the maximum output voltage which you are going to get during the positive half cycle will be equal to VCC minus VCE saturation, VCE saturation. The same as it in the previous case, class A amplifier. In the previous case, with emitter follower configuration, found this same configuration you are also going to see VCC minus VCN saturation. So this is the maximum positive voltage output. And now, so we can see the negative reverse biasing. So when the input voltage starts reducing from the during the before entering the negative half cycle, so it will come less than 0.5, 0.4, 0.3, 0.2, 0.1, 0, minus 1, minus 0.2, minus 0.3, minus 0.4, minus 0.5. So till the input voltage during the negative half cycle and during the negative half cycle, so from 0 to minus 0.5, so output voltage will be equal to 0. Why? Because the QP transistor. So now you have to understand it is a QP transistor. So this is the circuit configuration you have to consider. So QP is now it is going to turn on, and this QN will be in cutoff state. So because of QP, so output voltage you are going to get. And now it is also operating like it is also going to operate in the emitter follower configuration. So during the negative half cycle of the input, whenever it is going to exceed greater than 0.5, so you can see that for given input, as the input increases, the output is also going to increase in the linear way, and it is going to have a slope is equal to 1. So indicates what? So V naught by V in will be equal to 1. And then you can see the whenever the output the MOSFET MOSFET so whenever the QP, that is a BJT PNP transistor is going to be enters into saturation at that instant, so it is going to get saturated. Whenever it is get saturated, the output voltage will get saturated in this corresponding output voltage, that is minus VCC plus VCE2 saturation, VCE. So instead of 2, here we are going to mention it as P because it is a PNP transistor. So VCP saturation, VC. So here it is called VCEN saturation, VCE collector emitter, NPN transistor, N saturation, and here it is P transistor, PNP, so P saturation. So if you look at carefully the transfer characteristics, so you can see certain region of the input wherein which the output will not be having any constant. So it is output will not vary. So output will be stick on to 0, which is that. So during this band, so that is plus 0.5 to minus 0.5, you can see for any changes in the input voltage, you are not getting any output getting changed. So that is equal to, that is the output voltage is stick on to 0. So that is from plus 0.5 to minus 0.5, the region is called as a dead band. So in this dead band, why? Because so output is not increasing nor decreasing, hence it is kept at a 0 level itself. So hence it is called as a dead band. The same thing. So you're going to see here. So sketch out transfer characteristics of class B amplifier is shown in the transfer characteristics, and you can see Vi centered around 0. where both the transistors are cut off. So when Vi is equal to 0, so both are cut off, both the transistors are operating in cut off, and V0 will be equal to 0, and hence this deadband results in a crossover distortion. So this is the deadband. So why it is called as deadband? Because so any changes in the input voltage you are not giving to, it is not going to create any change, it is not going to change the output, so it is called as deadband. Is it clear? So it is going to be called as a deadband. So this deadband is going to cause the output distortion. When you are going to see the output, so during this time, so the output is going to have a distortion. You can see the distortion which you can observe here or here. So this is a VI, transfer characteristics curve. So in this transfer characteristics curve, so up to here this is 0.5 and this is nothing but minus 0.5, and you can see there is increase in the output voltage for increase in the input voltage. At the same time, for increase in the input voltage in negative direction, the output is also going to increase in the negative direction with a slope of 1. But during this stage, so what, there will be no change in the output. So output is equal to 0. So we can see this is the input voltage which you are going to give. So this is the input curve. So for this input curve, so during this 0 to 0.5, the output voltage will be equal to 0. So here you can see from 0 to 0.5, the output voltage is 0. And as you increase the input voltage, so here the input voltage is going to increase in this up to here. So you can see this region. So in this region, so the input as well as output is going to have increase as well as a decrease. Okay, so as your input voltage is increasing, so output is also going to increase. And whenever the input voltage start reducing from maximum value to this 0.5, so you can see there is the output is also going to reduce. After that, so during this segment to this segment, so you can see this is a 0.5, from 0.5, 0.4, 0.3 to 0, 0, minus 0.1, minus 0.2, minus 0.5. So you can see there is output is going to have a 0. So after that again you can see increase in the reverse direction. So this is the curve we can see. So this is the limit of crossover distortion. Okay, so from 0.5 to minus 0.5, so for any given input, so there is no output, so that is called as a deadband. So this deadband results in a crossover distortion in the class B amplifier. So this is the major drawback in class B amplifier with the complementary emitter follow. So complementary amplifier for the class B amplifier is considered. So crossover distortion is the major drawback. So, but you can see this is nothing but what? So this is the class B during because of Q and transfer, you're going to get 1/2 of the cycle. During the negative of cycle, PNP transfer is going to conduct, and hence you're going to get the output error because of a PNP. So this total for a given input cycle, you're going to get over here. But if you're going to consider only class B, so the operating angle will be only 0 to 5. So now we will see what is the power conversion efficiency in the class B amplifier. So in this class B power efficiency, so neta. So as I told, so what is the power delivered to the load we need to see, as well as power delivered by the AC supply and power supplied by the DC power. So ratio of this power AC power delivered divided by DC supply power, that gives the efficiency. So, to calculate the power conversion efficiency, we can neglect the crossover distortion, but we can consider the output sinusoidal peak. So, power dissipation, power load. So, power supplied to the load, we can consider as what? PL is the term, power supply delivered to the load. So, that will be equal to, so this will be equal to what? So, this is the V0 cap, or you can also write it as a, so this is a sinusoidal output. So, that is the AC power delivered to the load. So, we have to find out first PL. So, PL is nothing but V0 cap divided by root 2. So root 2. So V0, this is the maximum peak voltage. So V square by R. So this is the V0 square divided by 2. So V0 square divided by 2 times of Rn. So this gives the AC power delivered to the load. So what is with the this is about the AC power. Now we need to find out DC supply power. In order to find out the DC power supply, so since we are going to have two emitter follower configuration, because it is going to work with respect to NPN as well as PNP transistor. So current drawn from each supply we need to consider, because two power supply is considered. So this is a negative power supply, and this is nothing but a positive power supply. So this is negative power supply, and this is nothing but a positive power supply is considered. So the power supply delivered to the load will consisting of both positive as well as negative power supply, which is going to supply to the load. So DC power supply, so VCC. So from each of that, so power supply during the positive power supply, this is nothing but a power supply due to negative power supply, that is denoted as PS minus as well as PS plus. So what will be the current which is going to be drawn? So what will be the current? I will be equal to what? So I will be equal to what is the maximum output voltage divided by the load resistance, that gives the sine wave, that is the current expression, right? So the current supplied by the average current drawn from the power supply will be equal to V naught divided by RL. This is a half sine peak amplitude, right? So this is current in the expression. So you can see, so that is the V naught cap divided by RL. So V naught cap divided by RL. So thus the average current drawn from the two power supply will be equal to 1 by pi into V naught into RL. So this is the current. Okay, so this is the current expression which is going to be delivered because of positive power supply. So the positive power supply will be equal to what? Current, maximum current drawn from the power supply during the positive half cycle will be equal to current. So I will be equal to V naught cap divided by pi into RL. So V naught cap divided by pi into RL. So two power supply is there. So you will be having what? So V naught cap divided by pi RL for positive power supply as well as negative power supply is also V naught cap divided by pi RL. So these two are nothing but these two are the positive as well as negative power supply. So now there is a positive as well as a negative current which is going to be drawn. So power supply delivered is nothing but what? So V into I. So this is the current multiply with how much is the maximum output voltage from the VCC. So it will be equal to approximately equal to VCC. Okay, so maximum power supply during the positive or negative, it is equal to VCC or minus VCC. So positive power supply andre, so current is nothing but V naught by pi RL. So multiply with VCC, that gives them that gives the what? So that gives the expression for power supply for positive power supply. So negative power supply also it is going to remain same, V naught cap divided by pi RL into VCC. So this is the power supply delivered to the load, and this is the power supply AC power supply delivered to the load, and this is the power DC power supply. Okay, so DC power supply. So if you take the ratio of this over this, you will be getting the power supply delivered to the there is a power supply conversion efficiency, not to converter. So this is a positive power supply as well as negative power supply will be same. So total power supply will be equal to what? So PS plus PS minus. So 1 by pi V naught by, so 2 by pi V naught by RL into VCC. So this is the total power supply delivered, and this is the total AC power delivered to the load. And if you take that ratio, so you will be getting as what? So it is nothing but efficiency which you are going to get. So that is efficiency is given by pi by 4. So if you simplify this equation, you will be getting pi by 4 into V naught by VCC. So if the output voltage is going to reach to a maximum value of VCC, then you will be getting maximum efficiency for the class B amplifier will be equal to pi by 4. So pi is what? So 22 by 7 or 3.14 divided by 4. So that gives the conversion efficiency multiplied with 100. So that gives 78.5% efficiency. So class A amplifier it was just equal to 25% conversion efficiency. Class A with the transformer coupled class A amplifier it will be maximum power efficiency can be reached up to 50%, and class B complementary transistor configuration ಮಾಡಿದಾಗ, so we are getting 78.5%. The drawback from this here it is going to have what? You are going to have a crossover distortion. So this is the maximum conversion efficiency, and this value, so this is conversion efficiency is which is going to obtain from the class B will be greater than the class A conversion efficiency, which is just 25%. So finally we note that average power available for a class B output stage. What is the average power? So by substituting V naught is equal to VCC, if you are going to substitute, then you will be getting what? V naught if you are going to substitute here, so average power supply, so VCC square by 2 times of RL. So this is about the conversion efficiency for class B. So now for the power dissipation is considered. So how much power dissipation in the previous class A amplifier ಏನಾಗಿತ್ತು? So we have when input is there is no input signal was there, that is P when Vi is equal to 0. So you are getting what? VCE multiplied with IC. So that means the maximum power dissipation was VCC into I. So that was the maximum power dissipation you are getting. But in this class B amplifier, so that is a quiescent operating condition only. So you are getting the maximum power dissipation. So that is what here he has mentioned. So class A amplifier stages which dissipates the maximum power under quiescent condition, that is V0 is equal to 0 or Vi is have not applying any power. So that time is going to have a maximum power dissipation. But in this case, we will be not having that type of quiescent power dissipation. So why? Because whenever the input is equal to 0, so output is also 0, but there is no static power dissipation will take place in this class B amplifier. So in this class B amplifier, so whenever an input signal is applied, so average power dissipation by the class B stage is given by what? So power dissipation is given by power supplied minus load power. So power supply PS, that is DC power supply, and what is the AC power delivered. So if you subtract these two, that gives the power dissipation for class B. So this is the power dissipation which is going to be obtained for class B. So supply power is what? So supply power is equal to this expression. So 2 by pi V naught by RL into VCC. So 2 by pi V naught by RL into VCC minus of DC power, AC power delivered to the load, VL will be equal to V naught square by 2 RL. So if you subtract these two, so you will be getting this as the expression. So 2 by pi as a VCC. So 2 by pi VCC, if you are going to take it common, and we are going to find. So V naught max, this is the power dissipation. So this is 2 by pi times of VCC you are going to get. So each or of you are going to differentiating with respect to for a symmetric case, because we are going to consider the half of the power dissipated in the Qn and half of the power dissipated in the Qp, because so Qn and Qp both are complementary transistors. So half power dissipated through the Qn and the half so the total power dissipation will be equal to half 1 by 2 times of PD. So whatever you are going to consider here, so divide by 2, that will be the power dissipation, because each QN, PNP as well as NPN both answer is going to dissipate what. So we are going to have the half of the. So worst case, we need to find out the worst case power dissipation will be. So by differentiating this equation 13.22, so with respect to V naught, so if you are going to differentiate, so what will be the worst case power dissipation, we can able to find out. So and derivative of that equation should be equal to 0, and derive this equation. So 2 by pi VCC will be constant over here, and 2 by pi VCC constant, and V naught, if you are going to differentiate, we will be having V naught by RL means 1 minus V naught square means 2 times of V naught divided by RL. So if simplify this equation, so you will be getting the average power dissipation as 2 by pi times of VCC. And this is the V naught, so worst case power dissipation, and substitute this in this from worst case or maximum power dissipation, you will be getting 2 by pi square, which is square by RL. Okay. This is about the maximum power dissipation. So divide by 2 if you make, so that will be for NPN and PNP transistor respectively. So divide by 2 if you make, so that is for here for power dissipation for NMOS, so NPN, and power dissipation for PNP transistor. So this is square by pi square RL. So this is about the maximum power dissipation. So maximum power dissipation can be evaluated. So you can plot the figure. So maximum power dissipation. So power dissipation maximum, it will be reaching at you can see the power dissipation is going to keep on increasing up to here, and when the input signal, so whenever the output signal is equal to 2 VCC by pi, so or 2 VCC by pi, so you'll be getting the maximum power dissipation as equal to 50%, and that is the conversion efficiency. And as you increase the output voltage, so at whenever the input voltage is equal to VCC, so you'll be getting the maximum conversion efficiency is equal to 78.5%. So this is where for the maximum power dissipation and efficiency. So with respect to figure which I have shown right now, so I'll just discuss with this in tomorrow's class. So I'll just finish by tomorrow. Class B ಮುಗೀತು, class AB I can finish. So class AB also tomorrow I will be finishing, and I'll be just starting with the operational amplifier. Okay. So one half an hour class is just required to complete this third module. After that I will just start with the fourth module. Okay. So with this I'll just conclude. So any doubt is there, you can ask. Hello.
No doubt, sir.
Thank you. So I just uploaded